And welcome back to our cosmic journey. We are now going to ask the question, what are quasars? So when we start talking about quasars, the name itself started as short for quasi-stellar radio sources. Now, the discovery of radio sources that appeared to be these point-like areas, just like stars, came about with the use of radio equipment in the 1950s, kind of leftovers from World War II. Now, although a few astronomers would have predicted it, the sky actually turned out to be full of strong sources of radio waves. And as they improved the images that their radio telescopes could make, scientists discovered that some radio sources were in the same location as these faint blue stars. Now, no known type of star in our galaxy emits such powerful radio radiation. So then, what were these quasi-stellar radio sources? And to really get a good understanding, we first need to examine things through redshifts, which is kind of our key to understanding quasars. So the answer to this question about what quasars were really came when astronomers obtained visible light spectra of two of those faint blue stars that were strong sources of radio waves. Now, the spectra of these radio stars really only deepened the mystery, as they had emission lines, but astronomers at first could not identify them with any known substance. Now, by the 1960s, astronomers had essential experience in identifying elements and compounds in the spectra of stars. That's how we knew stars had things like hydrogen, helium, and some smaller amounts of heavier elements. Now, elaborate tables have been published showing the lines that each element would produce under a wide range of conditions. So a star that had unidentifiable lines in ordinary visible light had to be something completely new. So their astounding speeds that they were able to find showed that these radio stars could not possibly be stars within our own galaxy. Now, any true star moving at more than a few hundred kilometers per second would effectively be able to overcome the gravitational pull of the galaxy and completely escape from it. And it turns out that these high-velocity objects only look like stars because they are very compact and very far away. Now, astronomers have discovered objects with large redshifts that appear to be star-like, but also have no radio emission. So these observations also show that quasars were bright in the infrared spectrum and X-ray bands as well, and not all these X-ray or infrared bright quasars could be seen in either the radio or visible light bands. Now today, all these objects are referred to as quasi-stellar objects, or QSOs, or as they are more probably referred to as quasars. We have over 1 million quasars now discovered, appearing in the sky as stars, and their spectra are available for over 100,000. Now, all these spectra show redshifts. None of them are showing any kind of blue shift. And when we do see these redshifts, we find that they are very large. Another thing we noticed with quasars is that the quasars obey the Hubble law. Because one of the first questions astronomers asked was whether quasars obey the Hubble law and were really at the large distances implied by the redshifts. Because if they did not obey the rule that large redshift was implying with the large distance, then that meant they could be much closer and the luminosity could actually be a lot less. One straightforward way was to show that the quasars had to obey the Hubble law was to demonstrate they were part of galaxies, and that their redshift was the same as the galaxy that hosts them. Since ordinary galaxies do obey the Hubble law, anything within them would be subject to the same rules. And the way we did this was to rely on the Hubble Space Telescope to give us some observations that gave us the strongest evidence to show that quasars are located actually in the centers of galaxies. Now, there had been some hints that this was true with ground-based telescopes. However, the Hubble Space Telescope is not affected by any atmospheric interference or turbulence, and as such can detect the faint glow from some of the galaxies that host these quasars. Now, the reason is that quasars can outshine their entire galaxies anywhere from a factor of 10 to 100 times or even more. And when this light passes through its atmosphere, it is blurred by turbulence and drowns out the faint light from the surrounding galaxy. Now, quasars have been found in the cores of both spiral and elliptical galaxies, and each quasar has the same redshift as its host galaxy. A wide range of studies with Hubble Space Telescope actually demonstrate that quasars are indeed far away. And if so, they have to be producing a truly impressive amount of energy to be detectable as points of light that are actually much brighter than their host galaxy. Interestingly enough, many quasar host galaxies are also found to be involved in a collision with a second galaxy, providing, as we will see, an important clue to the source of their prodigious energy output. Now, if we look at this image here, we can see that this top left image is showing a quasar that lies at the heart of a spiral galaxy, 1.4 billion light years from Earth. The bottom left image is showing a quasar that is the center of an elliptical galaxy about 1.5 billion light years away. And the middle images are actually showing remote pairs of interacting galaxies, one of which of these is hosting a quasar. Now, each of the right images also shows long tails of gas and dust streaming away from a galaxy, and that long tail is actually because the galaxy contains a quasar. Now, such tails are often produced when one galaxy collides with another. So let's talk about the size of the energy source. Given their large distances, quasars may be extremely luminous to be visible to us, because anything that is far brighter than any normal galaxy has to be pretty bright. In visible light alone, most are far more energetic than the brightest elliptical galaxies. But as we just saw, quasars also emit energy at X-ray and ultraviolet wavelengths, and some also do radio sources as well. Now, when all their radiation is added together, some QSOs have total luminosities as large as 100 trillion suns, or 10 to the 14th luminosity of our sun, which is anywhere from 10 to 100 times the brightness of our most luminous elliptical galaxies. Now, finding a mechanism to produce the large amount of energy emitted by a quasar would be difficult under any circumstances. So when astronomers began monitoring quasars carefully, they found that some vary in luminosity on timescales anywhere from months, weeks, or even some cases days. Now, this variation is irregular and can change the brightness of a quasar by anywhere from a few tenths of a percent in both its visible light and radio output. Now, a quasar is at its dimmest. You have to understand, though, is still far more brilliant than any normal galaxy. Now, because quasars typically vary between getting brighter and getting dimmer over periods of few months, the region where the energy is generated can be no longer than a few light months, not light years, across. Because if it was any longer, it would take far longer than a few months for the light from the far side to reach us. Now, some quasars are, again, very, very rapidly, which means that their energy is generated in even a smaller region. Whatever mechanism powers the quasars must be able to generate more energy that's produced by an entire galaxy in a volume of space that, in some cases, is not much larger than our own solar system, which means these have to be in a pretty compact region. And now we do, of course, have some early evidence for quasars, because even before their discovery, there had been hints that something very strange was going on in the centers of at least some galaxies. Back in 1918, astronomer Hubert Curtis used the Large Lika Observatory telescope to photograph the galaxy Mazar 87 in the constellation Virgo. On the photograph, he saw what we now call a jet coming from the center or the nucleus of the galaxy. Now, this jet pointed to some strange activity that was going on in the galaxy's nucleus. Now, after decades of study, astronomers identified many other strange objects beyond our own Milky Way galaxy. And then these make up what we call active galaxies or active galaxy nuclei, or AGN. And we've, of course, talked about this before, but astronomers first called them by many different names depending on what sorts of observations discovered each category, but of course today we know these are all powered by the same basic mechanism. What all these galaxies have in common is some activity in their nuclei that produces an enormous amount of energy in a very small volume of space.